The next topic we're going to come to is conservative vector fields. These are going to be extremely important throughout the rest of the class. Notice that all the vectors that appear to be normal to the level curves from which they emanate. This was especially useful as we looked in the last example where we plotted some concentric circles in the xy plane, and we saw that the vectors fields that we had there were kind of pointing straight up, which would be perpendicular to the xy plane because they all had the k component. Because we know that this is one of the properties that we studied when we came across gradients, it's natural to ask whether the vector field f of x comma y, which is equal to 2xi plus yj, is the gradient of some differentiable functions. So is that always going to be the case? Well, not always, but for those that are. So if you can find a vector field that's represented as the gradient of some differentiable functions, we're going to refer to those as conservative vector fields. So this brings us to the definition. A vector field f is called conservative when there exists a differentiable function lowercase f such that our vector field is equal to the gradient of f. So when this happens, we refer to little f as the potential function for the vector field capital F. So if we have a vector field, if you can find some differentiable function that has that potential as its, that vector field as its gradient, then we refer to the vector field as being conservative. Let's take a look at an example. In example 4, they want us to show that the vector field given by the previous expression is conservative. To do that, we need to show that it is the gradient of some potential function. And I claim that the function little f of x comma y, which is equal to x squared plus 1/2 y squared, would work. So what we would need to show, f is conservative if f would be equal to the gradient of little f. Let's check this. If I go ahead and calculate the gradient of little f of x comma y, remember this should be the partial of f with respect to x, I, plus the partial of f with respect to y, j. This is going to be equal to the partial of f with respect to x is going to be 2xi plus the partial of f with respect to y would be 1/2 times 2y, which is just y times j. And if we look at it, sure enough, that is equal to the vector field. So the vector field f is conservative for the one given by 4a. It also turns out that every inverse square field is also going to be conservative as well. Let's suppose that we have an inverse square field. So it's related to, so we have the vector u, and it's some scalar of a constant divided by the norm squared of the vector r. We're thinking of u as a unitary vector here, so u is going to be some vector r divided by its norm. We saw this a lot earlier in the course. I claim that the function f of x comma y comma z, which is equal to negative k divided by the square root of k squared plus y squared plus should be z squared, is a potential for that vector field. Let's see if this is true. So in order to do this, we would need to calculate the gradient of f. We know that this is going to be the partial of f with respect to xi plus the partial of f with respect to yj plus the partial of f with respect to zk. This function f is symmetric, so we should be able to fairly easily compute one partial derivative and then pick up on the pattern to get the rest of these. So I'm just going to do one of them. Let me do the partial of this with respect to x. In order to calculate this derivative, we need to use the quotient rule. I have the negative k. I'm going to bring the negative 1/2 down. Leave the inside function alone. And then we need to reduce the power by 1. Negative 1/2 reduced by 1 will give us negative 3/2. And then from the chain rule, I'm doing a partial with respect to x. So I need to multiply by the inside derivative with respect to x. And that's going to just give us 2x. Let's make some more room. So if we go ahead and simplify this, we see that fx is equal to, first of all, the negatives will cancel, so this will cancel, make us a positive. This 1/2 will cancel with this 2. And what we're going to have left is we're going to have k times x all divided by, this expression is raised to the negative 3/2 power. We can move that down into the denominator as being to the positive 3/2. I'll leave it up to you to check this, but again, from symmetry, if you were to do the partial with respect to y, what you would end up getting would be ky divided by x squared plus y squared plus z squared to the 3/2, and the partial of f with respect to z is going to end up being kz divided by x squared plus y squared plus z squared to the 3/2. So when we put this all together, this is what we have so far. The gradient of f of x comma y comma z is equal to, first of all, notice that all of these have a k, so I'm going to just go ahead and factor the k out. We would have kx all over x squared plus y squared plus z squared to the 3/2 I. Factor the k out. Plus y over x squared plus y squared plus z squared to the 3/2 j, and then plus z over x squared plus y squared plus z squared to the 3/2, and that would be times k. Kind of a weird notation. I should, not to confuse the issue, but this k is a vector, this k is a constant. I know usually in class we tend to write most vectors with the arrow notation, but I said that with I, j, and k I wouldn't do that because they're so common. Here we kind of have that constant k that's being used. Perhaps it would have been better to call it c, but you know, this is the constant k, it's a multiple. This guy here is the component function k. Okay, so what do we do next? Well, I want to make it look like what we have above, and we can do that by kind of breaking out part of the denominator. In the denominator we have this x squared plus y squared plus z squared to the 3/2 power. We can rewrite this as x squared plus y squared plus z squared to the first power times x squared plus y squared plus z squared to the 1/2 power. which is the same thing as the square root. And then what we're going to go ahead and do is let's take and factor this thing to the outside. So right now, the gradient of f, or del f, is going to be equal to, we have the k that we factored out before. I'm going to pull this part to the outside, the x squared plus y squared plus z squared, and now it's going to be times x over the square root of x squared plus y squared plus z squared, I, plus y divided by the square root of x squared plus y squared plus z squared times j plus z times the square root of x squared plus y squared times k. And now let's take a look at what we have. This denominator, x squared plus y squared plus z squared, that is the norm of the vector squared. So that's the norm of r squared. And if we look at what we have on the inside, we have the vector xi plus yi, plus yj plus zk, that is being divided by its own norm. So this ends up simply being the vector u. It's a unit vector on the inside. And that's exactly what our vector field was equal to. So we've just shown that because the vector field f is equal to the gradient of this particular potential function, that f is a conservative vector field. So things that are governed by inverse square fields will be conservative.